Hello, everyone, and welcome to today's webinar, High Electron Energy Loss Spectroscopy at Extended Fine Structure. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We'll attempt to answer any questions for the speakers at the end of the presentation, but if we don't get to your question, we will follow up later via email. Now I'd like to introduce the speakers for today's webinar. Dr. Kelvin Chen is currently a senior staff scientist at the Imaging and Characterization Core Lab at King Abdullah University of Science and Technology. He obtained his PhD at the University of Manchester on energy dispersive X-ray spectroscopy quantification in the transmission electron microscope from 2011 to 2015. After his PhD, he became a postdoctoral fellow for atomic resolution imaging and atomistic level phase transformation pathways at Monash University and subsequently at Max Planck Institute for Sustainable Materials between 2015 and 2019. Afterwards, he moved to Thermo Fisher Scientific as a scientist for the TEM until late 2023. In 2024, he joined the KAUST Core Lab as a senior staff scientist, centering on the boundary of electron dose efficiency within electron microscopy. The second speaker is Dr. Xingxiao Wang. He's also a senior staff scientist at the Imaging and Characterization Core Lab at King Abdullah University of Science and Technology. He earned his PhD in Materials Science and Engineering from the University of Texas at Dallas. His research interests focused on the structural characterization of nanomaterials, employing cutting-edge electron microscopy and focused ion beam techniques. Now over to Dr. Chen.
Thank you very much for the introduction. I will just turn on the webcam for a couple of minutes, just seeing that we're not the artificial intelligence person talking about behind though. But later on for the internet connectivity, I'll shut on the camera just so that we are ensuring everyone can hear us properly. So now from now to on, I will use the camera, shut on the camera, and then I can start properly talking. So basically, these are the work we've done equally, and we're supposed to talk, initially planned to talk by two parts and to get more continuity. So I'll present the whole presentation throughout this time. And if you have any questions, and Xingxiao may work, we will get back to you on your questions. So today the webinar topic is the high energy loss, where especially we are focused on the extended energy loss fine structure. So in this presentation, we'll go through typically 5 parts, like why would we bother to do this, and what are the scattering principles behind, and what are the challenges to get this stuff been done. And also we'll go through the data quality assessment and fitting for the coordination up to, so to say, for show, basically. So if you look at the right side, which is the simulation results for copper KH at room temperature typically. So you can see what we're expecting from the extended energy loss fine structure. And those are just pretty much same as what you expect from the synchrotron EXAFS, which is just coming from the X-ray instead of the electron source. And what is the extended electron energy loss fine structure, which basically occurs when the electron is excited by fast electron to the unoccupied state to become free or quasi-free electrons. But mainly what we care about mainly here is the K-shell electrons, and which I will explain a bit later on. So basically what happens, if I'm wrong, please correct me. Basically what happens if you have the 1s electron or K-shell or L-shell, whatever, it doesn't really matter, but here we focus on K-shell. There's a reason for that. So basically when this K-shell electron excited to the unoccupied state, it will be left with a hole from the K-shell. And then you can also have, let's say this electron at L shell can also jump to fill up the hole, which you will see that from the X-rays like K of 1, K of 2, or K beta. And because you can only have that because there's a quantum selection rules behind that. There's the momentum transfer must be meeting with this quantum number minus plus 1. And in that sense, and the structure will be much more complicated, where instead if we have the yields, which would be much simpler, and that's why we are doing here. So basically, so there will be slight difference between metal and semiconductor or oxide and so on, just because of different band structure, basically. And because of that, you might see different extended fine structure, but that's not our major topic for the moment. So how this extended fine structure happening is that, as we said, the electron scales being excited to the unoccupied state. In that sense, let's say for copper, it will lose 8,900 electron volts roughly, and then you will get transmit electrons, which undergoes this elastic scattering by neighborhood atoms. That's where we see this escalation or interference you see over there. So that's where this modulation of the signal you've seen here, and for here is the simulation results. And why we chose K shell instead of L or Allen shell, which is basically because K shell is well shielded from valence electrons, and also pretty much shielded from the external field. So if we measure any phase shifts, that's a much cleaner than the other L or MH. L or MH, basically there's no spin optical coupling for 1s electrons, which literally means when you measure, when you compare the L edge and K edge, and then there will be much less overlapping and much easier to interpret. But also another reason that K shell holes typically have longer lifetime, which means you have also a bit more visibility for signals. And when we see these escalations, as we mentioned before, and then if you make FFT out from there, you will see this so-called radial distribution function, and you can use that to analyze the neighborhood atoms and so on, the information. So what we can get out from there? So literally, because there is the interference between neighborhood atoms, so you can, of course, measure the atomic distance or the resulting lattice, or any lattice change and between different shells as well. But you also can get the quantitative vibration mode without concerning much of the channel effect, which you often encounter by the elastic or any other L edge or M edge, because these K edge effects mainly dipole, and there might be sometimes a bit of a quadrupole effect, moment effects. But in most of the case, the channel effect, you basically can ignore that. So in that sense, it's a more quantifiable structural information, although it turns out it's quite complicated to quantify. But in terms of quantifiability, it's slightly cleaner to do so. So there is no critical difference between EXAFS and, in terms of the source and how we collect information, they are a bit different. But in terms of the formula itself, they are exactly share the same formula from this dipole effect, basically. And the slight difference over there is, if you look at in the formula, that if you look at the neighborhood atoms, it's not a purely neighborhood atoms, but because it's simply coupled with this called amplitude reduction factor, which may vary between X-ray and the electrons, because fast electron interaction with the K shell electrons and X-ray interaction with the electron are slightly different. And otherwise, the rest are the same, basically. And while we haven't done much yet, I think there are 3 challenges for us for the moment. And one is the projector optics, and the other is the GIF. And finally, the other big story is also how can you do the fitting properly. So hopefully today we can cover most part of this, hopefully. So talking about the projector, and these are just a simple schematic optics for the projection. So imagine that you have, okay, for those persons who do not know too much about the optics, so we're plotting the field ray and actual ray, and you can simply imagine the actual ray is basically the diffraction or angular information. For field ray is just in diffraction mode, and field ray is the kind of indication for you to say if that's in focus or not. For those persons who do not know much about this optic stuff. But anyways, that's not the key thing we're talking. So literally what I'm trying to say is, if we look at the 200 kV, let's say, or just a simple simulation to compare 200 kV and 190 kV, if you get one in focus and the other will be completely out of focus, and which, like you can see, they're nicely there, but if you look at the high energy, like copper, roughly close to 10K, you see this distorted page, which literally means the projector is not in focus. And also one thing to remember is that if we only care about this 190 kV, the effective cameras also change too. Although it might be good in some sense that you have better collection angle, but since it's out of focus, it doesn't really matter whether you have a good collection angle or not. So now if you start to align it, and if you want to make some theoretical prediction how much you can do, which literally you can make some simple simulation to say where the electron energy for 190 kV is in focus. And of course, the camera lens becomes a bit tricky now because the order of the, if you're doing the scaling properly, and the order of the camera lens just what between 200 kV and 190 kV. And so that's one thing to remember. And the other thing is that if you're manually doing this, so it might become a bit different. So you need to be mindful of the camera lens, because you want to maximize the signal from noise, or maximize signal as well, or make the best trade-off. So you need to be mindful of this, which camera lens you should use. And the other thing we have to bear in mind is that if we, in this case, this is for practical, let's say, warning message, that if you have a misalignment from somewhere where, let's say, there's a mechanic misalignment or any other optical misalignment, the effective camera lens can change due to this misalignment too. So you really have to take care of these effective camera lens and the effective collection angle of the signals, so that you can really maximize the output, because the K-shell excitation or the cross section are so that you don't have much signals. So so the microscope we're having here is the TEMS from thermofacial, and under this microscope we have free lens control that we can activate, and then after that, then you can either calculate or you can manually do that as well to excite your projector lens, so that you can, in such a sense, you can focus your energy over there. So these are the example that is the imaging or the 2D spectrum you've seen, and from the camera that if you manually align the system, this how this behaves. You are opening this, you can see a spectrum opening so that you can fully have an even, so to say, close to even, let's say, animation. So if you have a good eyes, now you probably can see the edge in focusing. You probably can see a few ripples there already, because these are very short acquisition, a couple of seconds. And of course, you also have to refocus the GIF, because you're literally changing the energy by 8 kV, I think 9 kV roughly. So you do have to refocus the focus. Literally, the lower vibrations, and mainly they focus X and Y to really. And there might be sort of stigmatism happening, but that's not a major concern. So now you can see this ripple populate there, which is the ripple or wig or oscillation you've seen. So you can have different naming. And if you compare this to the simulation, we did the simulation to include the electron source as well as the dispersion effect, which out from the camera and the optical setting we're choosing. So from here, you can see the near edge information quite properly, but also you can see the oscillation properly there too, which is very much consistent from what we simulated from the extended fine structure over there. But now our focus is more on the extended fine structure, where the near edge information is not our concern for a moment, especially for the K-shell information. We want to get the vibrational property and so on and so on. So in that sense, we care much less about near edge information. And so to summarize what we found, the key problem or the key issue we encounter is always the counts, just like beginning of 2000, where the counts for the X-ray are the issue about the EDS always counts. And now, if in this, the biggest problem always been to the how many counts you have to meet with the statistical signal to noise. And then with this, and before talking about this count and the counts for K-shell in EOS, and we have to say that the strategy we are using is to get the high energy core loss is we use a hybrid strategy to use both high tension change as well as the drip tube. And with this hybrid strategy, we can get energy loss up to 16 keV, which is pretty much we can really have a good signal to noise to judge, so to say. And because one can try higher, which we haven't tried yet, because we are a bit more concerned about KEH and have a good data quality, which can make sure we can interpret the data properly. So basically meaning that if you want to get 16 EV, for example, and then here you can go to 212, let's say 12 keV energy difference to change. So to say roughly. So that it's completely up to what you are choosing to do. And then you would have to, of course, align the projector system to avoid optical noise, as we mentioned before. And also you would necessarily have to have it not simultaneously, but you would necessarily have to, for the same area, have the zero loss peak for deconvolution, because in that sense, you can remove the multiple scattering effect from the extension and energy loss fine structure shape. And in that sense, it would be much better for fitting, which we'll talk about a bit later. And also, noise-free cameras are very critical to mitigate the recurrent electron beam damage, not only for signal to noise, but also you can do fast scanning, so that we typically do sub-millisecond scanning, so that it can accumulate enough signals without bothering about noise. And again, because we're talking about how many counts, how good signal to noise we can really get. So in that sense, we will have to go to a bit lower high tension, let's say 200, or at least that's what we chose to do so. And in that sense, the DQE of the camera for the lower high tension slightly, let's say, depending on how good sample we can have, is very critical. So in that sense, we do choose the Stella GIF camera to do this just because it's good for low high tension. And for this work, we also choose high dispersion, let's say low dispersion, I should say, which means 3 EV per channel, because we are a bit more concerned about signal to noise. And if you adopt same strategy, you use exactly same as the way said before. This is just camera rated, that's why you don't see the proper scale there. And you can see this exactly, not exactly same, but because they are different camera, but you can see the escalation or this interference signal on the 2D spectrum, same as we saw before on this K3 camera. And then you can extract the 2D spectrum out from there. So, and the data set, we come to the real data set we acquired on the copper KH, and the left side is the raw data set, which acquired at 20 kV, and we use 10 rods. I think you're encouraged to use lower, and we use the bit trade-off of the collecting angle of 45 to avoid any or to get the best trade-off for the scattering for the noise, signal to noise, basically. And the right-hand side is their loss deconvoluted data set. You can clearly see the advantage with the ZLP deconvolution out there, which you can see the deconvoluted KH shapes pretty much consistent from what we expect when we take into account the source and dispersion effect from the simulation. And you can also compare this to the X-ray absorption or EXAFS extended structure. They're literally quite much, and you can see it's the same or very much similar compared to simulation as well. And I think one of the advantage you can really say that it doesn't matter if there has to be in a reasonable thickness, but once you approach the reasonable thickness, and then with the DLP, their loss peak deconvoluted data set, you can be less concerned about the sample thickness. And of course, you will lose a bit of energy resolution compared to the EXAFS or the data from K3. But as I said, we're a bit more concerned about extended structure, and because that will affect the radial distribution. That will be dominating the radial distribution function, which we will get later on. Okay. This data set, by the way, I forgot to mention that the data set is pre-processed by Asana software, and the X-ray data is from my colleague Mark. And then, of course, you can integrate a bit more time so that you can get a bit cleaner signal. You can pretty much see they are having a very similar structure between X-ray and electron source, basically, and as well as the simulation if the source and dispersion effect included. Okay, and now we can turn over to the fitting, which is another big story we are encountering. So as I said, we are using exactly the same formula we are using. And this is we are using the Amity software for fitting. And those are the facts calculation where you can see from a typical and Amity software. And those are the paths that are included where there are a huge number of parameters you can fit for. And like third or fourth or immediate part of energy, which you don't necessarily have to care nowadays. I think there was from Lex reason, which not necessarily make too much sense. In my understanding, one can argue this differently. And as I mentioned before, the coordinate number and the amplitude reduction factor, they are very much coupled. So you cannot really differentiate them at each other at all. So we're just using this as a standard test. And then after you fit in, and one thing to mention is that here there are a few critical parameters you need to bear in mind, except this amplitude reduction factor, which probably alpha and mean square atomic displacement are more interesting for you, which alpha just represent how much it differentiates from the original lattice or original interatomic distance. And the sigma square, which is a very critical matter because it reflects the atomic mean square atomic displacement, which literally represents the Debye temperature, which is very much coupled with acoustic formula if you are doing this very properly. So by fitting the first shield, you can list our fitting and you just choose different parameters so that you can do the fitting properly. Of course, you also need to choose this parameter according to your dispersion and so on, so basically the optical setup. And you can see that the fitting results shows us like roughly, this is a very consistent number, we'll talk later. But this amplitude reduction factor is something like 0.6, which is a bit different from the X-ray, which is the 0.8 to 0.9 roughly. And that's literally what I mentioned before, there will be difference between electron interaction and X-ray electron interaction. Okay. And with this setting, you can include all over this path and fitting up to fourth shield. So in that sense, you would then, of course, because we are getting more shield to fitting and the statistics better, and then we have a slightly different in terms of the compared to the fitting with only one shield or only one with the first shield, which tells us how important that if you have a good data quality that can make you so that you can have this factor calculated properly. And also you can see the Debye temperature difference between different shield, which literally very consistent with what X-ray measures. The only difference that there is the systematic, let's say, reduced in terms of the Debye temperature because we are using the same foil, where the lattice is a bit different, so the vibrational property or the lattice has been relaxed a bit. So in that sense, you would expect the Debye temperature is going to be smaller. And nevertheless, you can see the Debye temperature change according to different shield, which means you cannot use you cannot approximate this atomic vibration as the purely harmonic oscillator. You have to include this anharmonic effect basically, and this can be a very good input for when you want to refine the first principle potentials basically. One of the key things I think we have to really bear in mind is that when you're doing the fitting, you are not only concerned about how good fitting visually here, but you also have to bear in mind either your reduced chi-square or your R factor, which has to be statistically significant. And you have, let's say if you got the R factor above 0.02 or 0.03, or yeah, that's a bad fitting regardless of how it is here. So you really have to bear in mind how good fitting it is by the statistical mass. And you might, if you carefully look at here, you might also see there's a bit, let's say, this fitting not as good. There are a couple of reasons we can talk a bit later on, but it's not key. The key thing, there are always some, when you're doing the fitting, there are always something you need, it's not as good as perfect, but you have to bear in mind those parameters are most important ones. And of course, you can also apply this to other materials, which we tried. Another one, the nickel, which we on purpose pick one of a data set which is not as good, where you have a contamination on the sample surface, and then you can see the fitting is not as good as you are expecting, although it does give us a proper train for the Dubai temperature. And if you're managing the experiment properly, chose the optical setting properly, and then you would be able to fit in the radial distribution function properly up to 4 shell. If you look at especially the real part, which is the criterion for the fitting, and you can see the similar trend. Of course, the better fitting is literally because we have much better signals. And previously, regardless of which one we are talking about, sorry, okay, cool. The original data set, I understand. So literally here you only see something like 8 to 9 escalations, but here you actually see roughly about 12 escalations. So basically, this just to address the concern that for what we previously mentioned, signal to noise the key, and we are more concerned about extended structures and extended structure basically. And we can also apply, this to alloy as well, and which is a copper nickel alloy. We also can fit up to 4 shell, and you can see that the Dubai temperature, which is fitted up from here, which just stand between copper and nickel as alloy, which very much consistent with what we found. And the reason we chose copper for fitting is just because copper, it first has more escalation, and also its tail doesn't have any further information to go, so that's a bit cleaner. And of course, you can also choose nickel KH to do the fitting as well. That's not a big problem. So to summarize, so we basically demonstrate if you properly align the projection and GIF and image filter, any other, can produce the high quality data on the extended fine structure, which is comparable to EXAFS. And to some extent, you probably have a slightly better quality in the sense of this, it can deconvolve the thickness effect. And although the energy resolution is much more limited, of course, in this case, and also electron beam damage is much more pronounced, which requires a bit more or have harsher or more demand on their sample preparations. And this extended electron energy fine structure can give us, as we talked before, quite, let's say, quantitative measure or quantitative measure of vibration property of different shells. And within the current framework, I think we can pretty much produce spatial resolution up to 20 nanometers, roughly. When we say this, not because they're limited by any probe size, they're really limited by the signal to noise, which is the killing factor for the moment. And using this, we can couple this into the acoustic phonon measurements. And yeah, so to the end, I also like to thank Mark and Georgian for our discussion and the X-ray data as well as the EM experimental design. And thanks, Gatan, very much for this Stellar GIF collaboration project and also the lab for the supporting. If you have any question, please. Thank you so much.
Thank you very much, Calvin, for giving that great presentation. A lot of good data, a lot of information for users to get started with doing these type of experiments. There were a couple questions that came in and that are coming in right now. I think the first one you might be already answered, but which code we're using to simulate the ionization edges in the extended fine structure?
It's a FAF calculation. You can use a FAF 8 or 9 or 10, regardlessly which one you're using. For the copper key edge, it doesn't give much. It doesn't give any difference, basically.
Okay. And how long does it take you to take or to do a calculation roughly when you're doing FAF code?
I think like 10 minutes max.
Okay.
Yeah. If you're not hunting for very precise calculation, which is also not quite necessary because we're not reaching that stage for very fine structural simulations. So unless you are really hunting for very fine structural simulation, which to my understanding currently is not necessary, in that case you can finish in 10 minutes.
Okay.
For sure. Yeah.
The next question that we have is, and I think you talked a little bit about this at the very beginning with your ray diagrams, but how do you take into account the chromatic aberration of the post-sample and spectrometer lenses for obtaining EXELFS above 2 keV?
To be honest, let's come back here. I think currently, no, I do not take into account any chromatic aberration effect, which I also don't think that's important for this extended fine structure, because if you compare the resolution we can get, which let's say, unless you are really talking about very near edge information, otherwise for extended structure, I do not think that will make much difference between one and the other, unless you are really acquired data set between completely different energy. And otherwise, the chromatic aberration is not critical at all, because the energy resolution we are talking about here is something like live or even worse in the case we're talking about. So I don't think that matters much.
Well, I think more of maybe they were worrying more about like the crossover. So the crossover occurs because your lens will focus energies or electrons at different energies. So you adjust the crossover using the free lens control, and then correct. Which I don't think that's anything to do with the chromatic aberration itself. I mean, of course, you let's say between the zero loss and the K and this K edge, of course there will be difference in folks, but that's a very, let's say, stable difference. So I'm not concerned about that for the moment. And especially for this high energy loss, we do not do simultaneous Julios or whatever. We just acquired data set of the zero loss first, and then go for the high loss. And especially when we're doing this resolution, which is not really up to super high resolution, which is not in any case doable, and this is not really a concern for the moment, at least. Okay. The next question was, are the oscillations in the fine structure or the extended edge more pronounced in these the deeper edges? So I guess as you get closer, as the S states become more tightly bound, as you go higher in energy loss, compared to the K edges that are below 2 keV. Have you looked at or done any analysis on any edges that were less than 2 keV in energy, or mostly stuck with the highest energy edges?
I don't think we have tried that, or probably haven't got much interest out from there, which is the 2 keV, which must be silicon or below, right?
Yeah, it'd probably be something like around silicon, yeah.
Yeah, we haven't tried that yet. And
I would think you would get similar results.
It should
if you had similar coordination numbers, yeah.
Yeah, but it would, for lower energy, might be optically even more difficult in a way, because you somehow mix with their loss signals. So it's not actually less straightforward to be very clean in some sense. That's my guess.
Yeah,
I'm not entirely sure.
Your signal to noise would definitely be larger, so your acquisition times would be shorter, right? So it'd be
Correct.
easier in that sense. Yeah.
In that sense, it's certainly better, but also their loss signals can somehow mixed in there as well. So because you're basically the scattering, the characteristic scattering angle are much lower compared to the high energy like 8 keV or 9 keV. So in that sense, you have a bit more mixed information there, I believe, and then it's even harder to get a very proper signal to noise. And this signal noise I'm talking is a scattering signal to noise, basically, I guess, but I'm not entirely sure with that. We haven't tried that. I'm just a bit my guess.
Okay, let's see, the next question is, what dispersions are you using for these experiments?
3 eV per channel.
3 eV per channel for stellar, like,
yeah. We want to cover the large energy range, so we try 3 keV.
Yeah.
If you want fine structures, you can try 1.5 or smaller, but in the single ones that main problem is count.
Yeah. And so basically, we just try to per pixel we get enough counts. If we're using 1.5, you will probably need to do the binning later. So instead, so we chose to not doing that way because physically doesn't make too much sense unless you want to do manual filtering or something probably. But we are not really, or we're probably a bit skeptical of that.
Yeah, so if you go to higher dispersions, you spread your signal over a larger number of pixels and see if they acquire for a longer period of time to get the same.
But it depends on how one designs the experiment. So you can't be there will be no singular solution or singular answer on this.
And the wiggles in the fine structure, the extended edge is pretty broad, right? So you probably won't gain a whole lot from going to a higher dispersion. And you also have lifetime broadening as well,
Yeah. We're not yet reaching the superior signal to noise yet so far at the moment. Especially, we have to use the 1 to 3 nanoamp to boost the signal to noise. So we also have to be mindful of this sample dimension. So in the end, this so far our compromise or trade-off.
Gotcha. So you input a large dose to get the weak signal out of there. Yeah, in a reasonable amount of time.
Yeah, and also this is only for copper, which is very robust metal compared to the most of the material.
Right. It's a metal, right? So it's tends to be a little bit more robust to the beam.
Yeah. So.
The next question is: Have you looked at, or are you looking into any analyzing the near edge fine structure at higher energy losses, or have you guys mostly concentrated or focused on the extended edge?
I'm not sure because I think I have a slightly different understanding on this. If I'm a bit interested in the near edge information, I more want to go to L edge or M edge. So that's why we didn't try the K edge E, or we tried a bit, but we're not really doing much work on that. I don't know.
Yeah, for current study, we study mainly the copper metal only. So we really have some copper oxide on the surface, some samples. So once we found a lot of oxide formed, so we affect our oscillations in the extended edge. So we will try to minimize this. That's why at this stage we care more about the extended structure, not the near edge.
Yeah. And also for near edge, we are not sure what information we can interpret out from there. And I mean, if that's oxide, then what more? I mean, it's just a matter of what more information we can gain up from there compared to the L edge and M edge, which we haven't have proper idea yet. So that's why we haven't tried yet. There are like two reasons.
Yeah.
The next question relates to more of, have you guys done any quantitative analysis? I guess that'd be kind of hard if you're looking at a pure metal.
Which sense?
Yeah, I think maybe they're referring to more if you've used like if you've used it to quantify the concentration of a particular element, but I think you guys mostly have stuck with the single pure metals and not any compound.
Actually, personally, I feel like that's not even quite possible to really, let's say we did something like copper nickel, but I think it would be very hard from simple escalation to tell the composition. Instead, we talk the zero loss and for the
for the quantification purpose, normally it's easier to use the energy edge close to the low energy range.
Yeah.
It's more precise.
Yeah, and also for this quantification, we're more care about the quantification of the vibrational. Yeah.
Not the chemical, just the structure information.
Yeah, we're just basically measure the composition from the low loss, and also we do know what's the composition of that, and then we use that as the structural configuration for fitting basically. And then from this extended edge, we're more towards this the bi-temperature fit, which we believe it has a very clear physics there. Basically, that's current for the current stage what we're thinking for the moment.
Let's see. What will happen? Let's see. Oh, sorry, I skipped a question here. Do you use detail in the illness at high energy loss K edges due to core state broadening? I think the lifetime is inherently large, so I think just the scattering process itself leads to broadening. So the features themselves are broad inherently.
Yeah, correct. Very true.
And then I guess the next question is, have you guys looked at the EXEFS for amorphous materials, or have these only been crystalline materials?
Not yet.
Not yet. We did have a plan for this. We
have limited material choice.
Yeah, if someone is interested in collaborations, welcome to send us some materials for collaboration or for test, if anyone is interested in this.
Okay. I think they were also kind of wondering maybe what would you expect what would happen in the oscillations, right? So if you're looking at like the radial distribution function, as you go out in radial distance, how those oscillations change if compared to from amorphous to a crystalline material.
Yeah. I think that I guess EXAFS was more. I think initially it's more for amorphous or those. I think at least as far as I know, it was done a lot on the mechanical glasses before, but that involves a huge number of simulation of the structural configuration, which is a huge amount of work. So for us, we pick some well-defined structure to do this, but of course, from the application point of view, metallic glasses or high entropy alloy would be a very good choice to do so, because it can explore what locally the structural or atomic or chemical environment could be, which can be a very good candidate technique for doing either metallic glass, which is probably many, or other like high entropy alloy, which I think that would be very ideal technique, because the metal can bear a lot of those to do so.
Mm-hmm. Right. There's a lot of disorder in those materials. Yeah.
Yeah.
Or potentially.
And we can also really see the debris temperature difference from that measurement too. So one can see how amorphous it is locally or non-locally or globally. Sorry.
The next question is, I'm not sure, maybe you'll know a little bit more about this, Calvin, but is H field more proper for D shells than other methods?
D shell, he means D electrons, right? Or what? Yeah.
Right.
D electron, okay.
D electron, I don't think the can you repeat this question, because I didn't really understand this question, to be honest. Sorry.
So I'm not sure the term H field, is that something that refers to the FEF code, or is that I'm wondering if they're talking about like simulating a spectra, like an L edge versus a K edge, or an M edge maybe, but I'm not sure.
Yeah, it could. I mean, so from a simulation point of view, can we do the simulation for that with the M edge or L edge or else, right? Is that what means the question?
Yeah.
Yeah, you can choose whatever shell you want to do. I think in the software I don't think that's a problem. You can always do that from a simulation point of view. I think I do suggest, if you want to do, if one wanted to do the EXAFS or EXAFS in the DEM, extended fine structure, energy loss fine structure, and I do suggest to do simulation in the first place before heading for any practical things, because otherwise you can be very much lost if you're not so familiar with the machine and not so familiar with the technique you are using. So if you're doing a simulation, you know what you're expecting, and then you can usually judge which can be wrong. At least you have a quicker judgment instead of try some random things, because there are so many factors in this experiment, so you really have to take into account every factor, basically.
Let's see, the next question, this is a good one. So have you guys tried, so it looks like you guys mostly have done 200 kV. Have you tried, is it better or easier to do the experiments at 200 or 300 kV? And have you tried any experiments at 60 or 80 kV?
We did have some plans, but
you have to balance, I guess. The main reason we don't use 300 kV is the damage. So that's at 300 kV at 299 base 399 is very fast.
Yeah.
So now we mostly choose 200 kV. Another reason why not try the lower kV like 80 or 60 yet, because energy range. If you try that one, for example, 80 kV, the largest dispersion is smaller, so you cover less energy range.
Yeah, from the filter point of view, but also if you get in, I think there's one more thing I want to mention, except that So it's this is the technique which is very sensitive to the sample contamination. So if you're at 80 or 60 itself, it's a bit more sensitive to the sample surface. So it's also required you to do the proper sample simulation, sample preparation tools. Yeah. But it's good to try, to be honest. We did plan this, but we haven't gone there yet. We haven't reached that stage yet, but we will certainly try this at some point.
Okay. Let's see. The next question from somebody from TFS. Soren asks, "What is the total dose for the spectra that you have showed? Have you guys been keeping track of the dose?"
We do, and depends on which spectrum we are talking about. So let's say for typical like this, we are using roughly 2 nanoamp basically for the electron beam itself. And the previous data set we're having here, we are using something like in total for this is about 10 minutes. And for the best data set we're having for this, okay, which one we're talking about? This one we're talking about, which we acquired the data set for 20 minutes in total. But we can also localize down to something, I believe, 1.5 nanoamp for 5 minutes, for 3 minutes or more than enough for fitting, basically.
Okay, so yeah, for each spectra, in order to get a high enough SNR, you end up having to acquire in kind of the order of minutes. Is kind of what you're,
in order of something like 3 minutes roughly.
Okay.
It's hard to really argue that because it also depends on the sample thickness. You have to have the best sample thickness as well. So sometimes we do use more, sometimes we do use less. And also, if we also encounter sometimes, like when you have a very thin sample, it's also not very good too. So it's
signal or something.
Yeah, so it's hard to make a very singular comment on this. Yeah.
The next question is like what considerations would you guys take into account if you wanted to extend this to other, they say, functional materials? So maybe like if you wanted to apply this technique to something other than a metal, what would some of the things you would do to go about planning the experiment so that you get the best data quality possible?
Well, I think there are two things: best data quality or reliability of the data set represent the true structure itself. I think there are two aspects. And let's say functional materials, I think it's much more sensitive to beam damage, right? I guess.
Most of them, yes. Yeah. But another thing is like for like some functional materials, not other than metals, you maybe more care about the near edge features. So we need to think about use smaller dispersion to find the more fast for us.
I totally agree, because then the edge information is much much more useful in that sense, because I doubt the extended structure can give too much information out from there. Let's say copper oxide, and I don't think we gain much insight from the extended structure in our take, let's say, or at least from our experimental data. We did some data set for the extended structure as well for the or maybe our experiment system. Our resolution is still not yet reaching that level yet, or signal-wise, but in whichever sense, I think if for hard for copper oxide, it would be hard for the other as well. Also the beam damage is I suppose be quicker and can drive the oxygen atoms away, which I'm not sure how much it can reflect the true structure of itself before damaging. So, or it's hard to judge its damaging, right? Because I mean, especially for the 1 nanoamp, 2 nanoamp, or sometimes maybe even just higher current. So
Right. Yeah, you're definitely, there's going to be some limitation in terms of how sensitive the sample is to the beam and how small of a resolution, or how high of a resolution, I should say, you can get.
But this is a good point, because recently we think about we use even faster, because it's the direct detector electron detector is very decrease so high, so we can use faster scanning. And longer time keep roughly keep a similar total dose, but can improve the data quality.
Yes.
And reduce the damage.
Yeah. I think you're talking about if you do the fast scanning, and then the beam damage can be reduced a bit.
Yeah.
We haven't quantified how much, but we can see a clear signal of the mitigation of the beam damage out from there. But still, for the oxide or similar funky material, one has to be very careful doing that. Or maybe it's a good idea to do some bit more close to in situ experiments, or somehow like that, so that you can really see when the beam damage starts, and then you cut that slice off, and thereafter out from the analyze. Otherwise, you might get fitting, because in the end, you really care about the fitting quality. If you don't have a fitting quality, let's say this, then whatever data it is, it's just the data. So in the end, this is the final criterion, if whether you can fit the radial distribution function properly or not. If you can't, and then literally means the data has some issues. And also, one more thing to mention is that for fitting, you should use least possible parameters, and you should not change much of parameter. If you change too much parameter to do the fitting, although you can get a very good fit, but it's not a physics fit. So yeah, one have to be very careful of the fitting itself.
Pay attention to the.
Sorry, I don't want to. Don't get me. I'm not trying to say bad things about that. Just trying to say one should be very careful of the data interpretation, basically.
Okay. Let's see. A couple more questions here. So the question about the H field. So the attendee had clarified. They want to know if the magnetic field within the objective lens is affecting the band structure enough that your EXAFS would be compromised in some way. So it wouldn't. Basically, the magnetic field is altering the unoccupied or the density of states, and so that the oscillations in your EXAFS are changed by that, and so it doesn't represent the true structure. But I think from the simulations that you show, which don't take into account any changes in the band structure due to the presence of a high magnetic field, that it's if there are changes, they're too subtle for the technique to observe. And
if you are talking about K-shell, I don't think the magnetic field with something like 1.7 to 8 or 2 Tesla can change much of that.
Okay, maybe something more in the
compared to the atomic force. The Coulombic interactions to me.
Mm-hmm.
But I have to admit, I never done the simulation to take into account somehow around the 2 Tesla to see whether that really affect or not. But I doubt that can affect much.
And then the last question that we have is using EELS and EXAFS. Is there a way of detecting the nearest neighbor in crystallographic state of a completely new material? So I guess if it was a complete unknown.
You certainly can, but you have to build enough configurations to compare.
Right. So you'd have to have some complementing data like XRD or something like that to guess some
not only
crystal
that,
structure.
but also from simulation point of view. I can give you one example with a copper nickel alloy. So in that sense, you need to build a number of configuration to see which you fit best. Basically, that's how we do the work. So if you have a complete new material, you have a new large number of configuration you need to try to see which fits best, to see if you really want to get in that way. But of course, you can go to a bit more reduced way to estimate that can happen as well. So it depends on how good you want to go. If you really want to go very extreme, and then that's a huge amount of work for build a configuration, atomic configuration, and simulate and compare that to the real data.
It's really challenging for new material.
Yeah.
Normally, we need some pre-knowledge. For example, use low energy range to find the combinations. They can narrow down your guess.
And also, if you look at here, the paths. So these paths are totally dependent on the configurations, the atomic arrangement. So that's a very hardcore problem. Yes. So yeah.
Yeah, it would take a lot of iteration, right? You'd have to guess what the structure is and then make a simulation, and then if it doesn't fit, alter the structure in a way that the simulation would fit, and then kind of iteratively do that until you converge to some minimal difference between your simulation and the
even that you cannot really pinpoint that's a structure. You just say, okay, this is most likely this is the structure, but that's a likelihood instead of an absolute answer.
An absolute, yeah.
Oh, I mean, there's no absolute answer anyways, but I just mean to say, I mean, down to per atom, and to really precisely know him. But for complete new material, and it would be very hard to really be doing that, to be honest. It's more for
Oh, go ahead.
No, I mean, it's just more for you want to get a very refined, quantified structure or other information up from there instead of the complete new material.
Mm-hmm.
But you can get a lot of the quantifiable information out from there. Like this is the biotemperature measurement under different shell, and how, and of course you can couple that to the vibrational properties from the acoustic phonos and so on, which is not something you can measure by other technique easily with the spatial resolution and so on. So I think it itself has a very strong advantage, but it's certainly not for something completely new. Well, it can be, but you really need to do a huge amount of work to work it out.
Yeah, there might be some other methods maybe you'd have to try first.
Yeah. I guess that would be life easier, so to say.
Yeah. Okay. Well, I think I think that was quite a number of questions, and that was kind of the end of the list there. So I think we're good to wrap up now. So thank you, Calvin and Xing Shao for putting everything together. This is great. This is great work. Very promising results, and very, very informative. So I hope everybody can come away with a little bit of a better idea of how to tackle these experiments using yields.
Thanks everyone.
Thank you
for joining us, and hope that you get a bit of the useful information up here. If you have any questions, also just reach out to us, and we can try our best to. If you had any concern, we can try our best to address your concern.
Alrighty. Well, thank you very much, guys, and have a good rest of your evening.